All right, so what you can see here is the work that we just recently did on the combined gas law. So the next thing we need to talk about is the ideal gas law. And the ideal gas law looks at this combined gas law and says, you know, but this is messy. I have to have like all these initial conditions to predict the final conditions. I'd just like to know, like, if I have a pressure and a volume and like I know how much stuff I have, I'd like to be able to just calculate the temperature, right? Now remember, all of this comes from these relationships that we looked at, where we said this was proportional to that, and this was proportional to that. So for instance, we said we got to this by saying that the pressure was inversely proportional to the volume, or the pressure was directly proportional to the temperature, or the volume was directly proportional to the temperature. So for the ideal gas law, we come over here and we basically say, all right, let's take a step back here, and we know that the pressure and the volume are directly proportional to the temperature. And that puts the pressure and volume inversely proportional to each other, right? And the Avogadro's law also says that your volume is directly proportional to the number of moles. I'm going to put a little n there. That was the one that said, hey, look, this is interesting. Doesn't matter what gas you are. If you all have the same number of moles, you have the same volume of space, right? So we know that pressure and volume directly proportional to the number of moles and the temperature, which is, if we put a little constant in here, we can say the pressure and the volume is equal to some constant times the number of moles times the temperature. Now, if we have accounted for every variable here, at this point, we should just be able to find out what that constant is and then plug it in. And that's exactly what they did. And so they said, all right, so here's our ideal gas law. PV equals N for number of moles. R, T, where R is the constant that they discovered, right? That they said this should work. And so then they measured this with a lot of different gases, and they discovered that, in fact, there was a value here that was constant. And R, again, I will give this to you. It's in your equation sheet. R is equal to 0.0821 liters atmospheres per mole K. Now, these are just the units that are required to make this work. And you can actually find R in a lot of different units. Of course, if the units change, then the value changes. But I'm giving you this one in these particular units. And on your equation sheet, I also do give you the ideal gas law right here. Zach, that is a great question. Zach says, why don't we use capital M for moles? I don't know. Capital M is often used to mean some other different things, so maybe they're just trying to avoid that. So they're using a little n for number of moles. So again, we'll just put this out here. P is pressure, V is volume, N is number of moles, R equals the ideal gas constant, and T equals temperature. And I think it's molarity, yeah. Erica. Yeah, capital M is used for molarity, which is a unit of concentration, which we'll actually talk about on Thursday. So your lab is not too far off from where we are in that. All right, so in this case, because I'm giving R in liter atmospheres per mole K, that tells you that your temperature must be in Kelvin. Your moles, of course, must be in moles. It's not. But your volume must be in liters for this particular equation. And your pressure must be in atmospheres. You guys with me so far? Yeah. Okay, so next, all we have to do is take a problem and plug it in. And actually, this is a little bit easier than the combined gas law, I think you'll find, because the combined gas law has 6 different variables and it's got stuff on the bottom you might have to solve for. Whereas this only has 5 variables and nothing's ever on the bottom. So that's like obviously, not obviously, but it's just like on the outset, it's actually a little bit easier than the combined gas law. I should probably let you guys know what we're talking about here. So this is the ideal gas law. And this is the one that I actually do give you in your equation sheet. Something else to notice from here, by the way, is if you have the ideal gas law, you can determine the combined gas law from it, right? So instead of just memorizing the combined gas law, you can look at the ideal gas law and say, okay, hang on a second. If I have the same sample of gas, then N is the same, so I can cancel it out. And R, of course, is a constant no matter what, so I can cancel it out. So in the same sample of gas, PV equals T, and then you just move that over and say, okay, P1 V1 over T1 is constant. So P1 V1 over T1 has to equals P1 P2 V2 over T2. Does that make sense? If you're paying attention, and I gave you the ideal gas law, you should be able to get the rest of those gas laws just out of it. If that didn't make sense, then just memorize the combined gas law. That'll make your life a little bit easier. All right, but let's solve this problem. This will be, I think, even easier than what we've been doing. So here we go. This is from your lecture notes. If we have 3.5 moles of oxygen with a volume of 27 liters at a pressure of 1.6 atmospheres, what is the temperature of the sample? So they gave us, there's moles of N2, so that's N. That's liters, so that's V. Here's atmospheres, so that's P. And they want to know T. Okay. And then R is a constant, so it's just, that's R right there that we need. All right, so when I look at this again, I'm going to solve it first. I want to solve for T. In order to solve this equation for T, to get it on top by itself, I'm lucky it's already on top. It's not like divided by T, so I'm just to get it by itself, I'm going to divide both sides by NR. And when I do that, of course, they'll cancel out right here. And I'm left that T is equal to PV over NR. And now I just plug that in. P being 1.6 atmospheres, V being 27 liters, N being 3.5 moles. Whoops, 3.5. And R being 0.0821 liter atmospheres per mole K. Ooh. Okay. And then if I'm watching my units, hopefully you guys will see my atmospheres are divided by atmospheres and my liters are divided by liters. And here the moles are on the bottom, so I need to be, this moles are divided by those moles. And what I end up with is 1 over K. And when you divide by a fraction, the rule is you end up flipping it, right? So 1 over K, which this is, whoops, is the same thing as saying 1 times K over 1. Which of course is the same as K. I'm not sure if you guys remember that property of fractions. So our final units will be Kelvin, which is what we are looking for. We solved for temperature. So we should just plug that in. 1.6 times 27 divided by 3.5 divided by 0.0821 gives me a temperature of 150 Kelvin. You guys follow what I did there? Right, Sarah. So because R was in these units and we canceled out the liters in the atmospheres and moles, we're left with units of Kelvin. And just like in all of our other gas laws where we had to use Kelvin for temperature, we have to use Kelvin for temperature in the ideal gas law too, including R. And so that's how we know our unit is Kelvin. Now from there, we can convert that to Celsius, minus 273.15 and say I'm at minus 123 Celsius. Yeah, chilly. But that is what it is. Okay, let's look at our worksheet here. Okay, if I have 18 grams of oxygen at a temperature of 350 K and 550 millimeters of mercury, what is the volume? So here, hopefully you can see, they gave me, let's see, mass, temperature, and pressure, and they want volume. There's not, for these problems, you'll note, there's not a before and after, right? They don't say the initial volume was this and we want to know the final volume. That is your dead giveaway that you're not using any of the other gas laws. All of the other gas laws are comparative, right? Initial conditions to final conditions. But this is just says, nope, if I have some of these answers, if I can tell you something about the pressure and the temperature and the number of moles, you should be able to calculate the volume. So, all right, want to know volume, and again, I always recommend solve for it first before you plug anything in, which is exactly what Sarah has done, right? We're going to solve for volume by dividing by P, and that cancels. So we get V is equal to nRT over P. Okay, so we want to plug this in, but we have something else we need to do. And that is, we have to convert, from mass to moles, because R is in units of liters, atmospheres, moles, and Kelvin. I have to make sure that I am also in units of liters, atmospheres, moles, and Kelvin. Since I'm solving for V, that'll be in liters, but for my P, that needs to be in atmospheres. And my gas has to be in moles. And my temperature is already in Kelvin, so this checks out. Okay, gonna have a little, we're happy about the Kelvin. Yeah, so in order to solve this problem, we need to convert both of these. Now, if you're paying attention, if you don't consider that and you just plug it in, right? And we say, okay, 18 grams oxygen multiplied by 0.0821 liter atmospheres per mole K, and multiply that by 350 K, and then divide all of that by 550 millimeters of mercury, then hopefully you'll see before you continue that you have a problem, right? Because you'll note, okay, my Kelvin cancels with my Kelvin, but oh crud, my atmospheres don't cancel with millimeters of mercury and my grams don't cancel with moles. Does that make sense? So if you forget to do it before you write it out, if you always remember to write out your units, then the units will tell you, hey, don't forget to do that thing. Okay. Sarah has already calculated the moles of oxygen. How did you do that, Sarah? Just to remind us, this is from chapter 6. You all need to remember how to do this. 18 grams of oxygen. We just looked at the molar mass on the periodic table, which, because oxygen has 2 oxygen atoms, it's 2 times the mass which is listed, which is 16. So that gives us a molar mass of 32 grams of oxygen in every 1 mole of oxygen, except you guys were smarter than me and you put the grams on the bottom. There we go, so they would cancel. There we go. It's a pretty simple conversion, but you have to remember what you're doing, to do it. Okay, so 18 divided by 32 gives us 0.5625 moles of oxygen. Perfect. Excellent. So I'm just going to move this guy over. Insert right there. Parentheses. Okay. And great, then we need to convert, that's right, we need to convert our millimeters of mercury to atmospheres. Because we were good on this, now that our moles will cancel. And look, the moles cancels. The O2 doesn't. We're going to leave the O2 there. Okay, so to convert from millimeters of mercury to atmospheres, again, this is given to you on your equation sheet. You don't have to memorize this, but 760 millimeters of mercury is equal to 1 atmosphere. And then you just kind of need to know how to put that together. It's just dimensional analysis, right? You take the 550 and you're going to 1 atmosphere is 760, and millimeters of mercury cancels. Whoops. When I plug that in, we get 0.723. You guys are right on. Yeah, 0.724 millimeters of mercury. Okay. So, wait, excuse me. 0.724 atmospheres is the unit that's left behind, Mary. Atmospheres. I was about to copy that over to my equation, and I'm like, but I had millimeters of mercury to start. Okay, so we put that there. And now our atmospheres cancel. And when we are done, we will be left with liters of oxygen. See, the oxygen didn't cancel. Liters of oxygen on top. Perfect. All right, Sarah got 22.33. Let's verify. 0.5625 times 0.0821 times 350 divided by 0.724. Yep, 22.33 liters of oxygen. Perfect. How do you guys feel about that? Okay. Well, I'm glad you feel good about that, because we're going to take it another step further. You guys excited? Okay. So one thing that I did here on this particular equation is I brought back this piece from, was it chapter 6 on mole to mass? Because I was like, look, if I've got moles, I can get grams instead, right? Because then you can go from grams to moles. Just remember how to do that. Well, I can take it even a step further and put this together with a chemical equation and stoichiometry. Because if I can solve for moles of something, then I can solve for the volume of that gas. Haha! We can do it. Come on, this is the best. This is the best. Because you guys are going to do this and then you're going to feel so dang smart. And you should. Because you are. Okay. So this one, this is from your worksheet. And I did it in steps so you could kind of see the steps. And then, but of course on the exam I don't have to give it to you in steps. But I'm just, kind of walking you through it. So the first step here is to do a gram to mole conversion. So this is just from chapter 6. You've already done that before. And then in the second step, I'm going to take this number of moles and plug it in with this information to tell what the pressure is going to be based on the ideal gas law. Does that make sense? Won't this be fun? Yes, let's do it. Okay, this is easy. You already know how to do this. You've taken this test, right? Easy peasy. Except, wait, just to be sure, I know that each step is easy, but still it'll make me feel better to have the roadmap, right? So I'm going to bring over the roadmap, our favorite little guy here. Gonna put him, I don't have any space for my roadmap. Let me move this guy over. Okay. All right. So I'm just gonna say my aluminum sulfide, I'm gonna call that A, and my H2S, that's gonna be B. So they gave me grams of A, so they gave me this guy, and now they want moles of B, so they want this guy. Okay, so my roadmap says my molar mass is gonna get me here, and the coefficients is gonna get me here. All right, what shall I do first? Okay, Erica and Nicole say balance the equation, and Sarah says let's find the molar mass of aluminum sulfide. It doesn't matter. You're gonna have to do both of those. Doesn't matter which one we do first. But let's balance the equation. We have 2 votes for balance, so let's do that. We have aluminum sulfide plus water. All right, help me out here. I see 2 aluminums on the left, so I'm gonna put a 2 here. And then I've got 3 sulfur atoms in the reactant, so I'm gonna put a 3 in front of my H2S. Okay, and that gives me 6 hydrogens plus 6, so I have 12 hydrogens and 6 oxygens, so I'm gonna put 6 in front of my H2O, and that should solve the problem. Does that look good? Little 1 here. Okay, all right, and now that we've balanced it, we're gonna calculate, we want the molar mass of that Al2S3. I'm gonna bring my periodic table over here. I need 2 aluminums, that's 26.98, plus 3 sulfurs at 32.07 each. Okay, is that what you guys got? 150.17? Hopefully at least one of you guys did that. Okay. It's not science if only one person's doing it. You have to share and confirm. All right. Al2S3 is 150.17 grams in a mole. Okay. Okay. Oh, it's a little bright. Okay, so we have the molar mass. Now what shall we do? Set it up. Okay. If you're feeling lost, remember that's why I give you the roadmap, right? And you just reorient yourself. I gave you grams of A. We're looking for moles of B. So the roadmap says, hey, use the molar mass to get to moles. Okay, so starting from 5.7 grams, Al2S3. It says use the molar mass, so that's what I'm gonna do. Good, 1 mole Al2S3, 150.17 grams Al2S3, okay. So after I use the molar mass, my roadmap says I should be at moles of A, which in fact, those cancel, and I am. And then it says use the coefficients to get to moles of the other thing you're looking for. In this case, it's H2S. So I'm going from here to there. So I'm using these coefficients, a 1 and a 3. Perfect. And what's going to go on top? The H2S is going to go on top. That's what I'm looking for. But also, I want that moles of Al2S3 to cancel. Perfect. So if I do that, my moles of Al2S3 cancel. I solve for moles of H2S, and that is exactly what they wanted, so I can stop here. Don't be tempted to keep going. Don't need to. So 5.7 divided by 150.17, multiply that by 3, gives me 0.114 moles of H2S. Is that what you guys got? Oh, I see. Yes, you did. Okay. So that brings us to this next question, which says, this gas is collected in a 2.5 liter container at 1.5 degrees Celsius. What's the pressure of the gas in this container? Okay, cool. Well, I'm talking about a gas, and they gave me liters, and they're looking about pressure, and there's not like initial or final conditions, so you can predict you're going to use the ideal gas law, PV is equal to nRT, to solve this problem. And this is your N, and this is your V, and this is your T, and they want to know the pressure, so that's what you're going to solve for. And then of course you will remember, and you don't have to remember because I give it to you, that R is 0.0821 liter atmospheres per mole K. All right, so as Sarah noted, we're going to solve for pressure because that's what we're looking for. So I'm going to divide both sides by volume, and then the volumes will cancel and I'll have pressure, right? Volumes cancel, P equals nRT over V. All right, so I could just plug this in. Okay, wait, there's a step that we missed. I think there's a step that we missed. Yeah, Nicole is right. We have to convert from Celsius to Kelvin. So 21.5 plus 273.15. Let's see. So that becomes 294.65 Kelvin. Is that what you guys got? Yeah. Oh, sorry, 294. That's what Erica and Sarah were trying to say. I missed that. I thought, yeah. Okay, so we're gonna plug that in. All right, so now we can plug it in, right? So N is 0.114 moles of H2S. And R is 0.0821 liter atmospheres per mole K. And then T is 294.65 K divided by V, which was given at 2.5 liters. Okay. And if I do this, liters cancels with liters, and moles divided by moles cancels, and Kelvin divided by Kelvin cancels, and I'm left with units of atmosphere. So that should be good. 0.114 times 0.0821 times 294.65 divided by 2.5 gives me perfect. We're all in agreement. 1.10 atmospheres of pressure. What do you guys think? Was that fun? Maybe my definition of fun is different from your definition of fun. But what we get to see is that now we can take our little roadmap and we can go off-roading in this direction, any direction, not just off-roading. But for gases specifically, if you have moles of gases, you can convert to pressure or volume or temperature of that gas. Okay. Need more space here. Using the ideal gas law. Okay. Maybe I need smaller font here to make this work. Use a different color so it'll be clearer. But we're just using PV equals nRT, right? To get there. If I have number of moles, which is N, and I have any one of the other ones, we could just plug it right in, and we're just off-roading. That's not too bad. It's not too bad, and it was kind of fun. All right, I'm gonna give you guys a 5-minute break, and we'll come back and do another one of these, okay? For fun and profit, mental profit. But I'll give you about a 5-minute break to, I don't know, go scream at a pillow if that's what you're feeling like doing now. All right then, are we ready to try this again? Okay. So here we go. This is again from your worksheet, and I need more space. Apparently I'm out of space here. That's what happens when you put a whole chapter's worth of lecture in one place. Start running out of space. Okay. Scroll over here. So here's our, I'm gonna leave this here. Standard volcano demonstration at an elementary school employs the following reaction. You take, this is vinegar, with the acetic acid in the vinegar, combine it with baking soda, and what you get is this aqueous solution of sodium acetate, and the carbon dioxide gas is what causes the bubbles, and you make liquid. Okay, so if the demonstrator starts with 20 grams of dissolved acetic acid in water, what volume of CO2 gas will be produced at 298 K and 0.95 atmospheres of pressure? Okay, so in this case, if I'm using my roadmap, it's actually looking the same, right? We're starting with 20 grams, so we're talking about mass of, we'll call this A, and they want the volume of CO2, we'll call this B. So we're gonna go from grams of A all the way to volume of B. We're just going to use the same path that we did previously. We could do that. What do we need to do first? AMU, right? So if we're going from grams all the way this direction, the first step is to use the molar mass to convert to moles. So we need the molar mass of C2H4O2, which is going to be 2 times 12.01 plus 4 times 1.008 plus 2 times 16. Is that what you guys got? 60.052? Okay. Okay. So that's the first thing we need to make this first conversion happen. So we're putting this in our line, 20 grams of C2H4O2. And what do I do with this molar mass that I just calculated? Yeah, we're going to put the mass at the bottom. Good. Great. Okay, now what? Coefficients. Okay, perfect. Yes, so we got to here. Now it says to go here, we need the coefficients of that balanced equation. And we're going from 2 moles of C2H4O2 to, this looks like it's balanced because I do have some numbers here. So it should be 1 mole here. Did anybody verify, is this actually balanced? 4 carbons. No, 5 carbons. 5 carbons. 8 hydrogen atoms. Not in fact balanced. 8 hydrogen atoms. 7 oxygens. 4. I don't know about this. Oh, wait. 8 oxygens here. There's 6 there. Oh, it is. Okay, it was balanced. I got lost. I was very confused. I was confusing myself. It is balanced. 2 sodiums, 2 sodiums. I've got 4. That's 7 oxygen atoms. Here I have 4, 5, 6, 7 oxygen. Okay, it's good. It's good. All right. Oh, crisis averted. Oh. Okay, so now we're going to say we have 1 mole CO2 for every 2 moles C2H4O2. When you guys first learned this, I know that this was a little bit scary, but is this still scary? Or are you guys like, it's actually all right now? Oh, there was a grams here. Cancel. Okay, moles. Cancel. Okay, so that gives us moles of CO2, which is where we're supposed to be. And now this is an equation, right? An algebra equation. So we have to stop. We have to get off of our dimensional analysis wagon here, so we can plug it into our algebraic equation. 0.165. Oh yeah, that's what you got too. Good. All right, so now we're going to use PV equals nRT. And I'm going to solve for volume. So that's what they want. So divide both sides by pressure. Cancels. Okay, so V equals nRT over P. And so I'm just going to plug my stuff in. N, I just calculated, 0.165 moles of CO2. R, I give that to you. T, oh, they already give it to us in Kelvin. That's so nice. Look how nice I am. By they, I mean me. Haha. Okay. And P on the bottom, 0.95 atmospheres. Also, don't need to convert that because it's already in atmospheres. I can be nice sometimes. Erica says, on the test you won't. I know you won't. You're probably correct. I won't deny it. Atmospheres divided by atmospheres cancels. Moles divided by moles cancels. Kelvin divided by Kelvin cancels. I'm left with liters on the top, which is just what I wanted. Nicole got 4.2 liters. Let's see if that's what we got. 0.165 times 0.0821 times 298 divided by 0.95. Wait. I'm off by a little bit more, so I'm going to double check this. 0.165 times 0.0821 times 298 divided by 0.95. I'm getting 4.25. Okay. All right. We all got the same. Perfect. 4.25 liters CO2. Perfect. All right. So that is about as hard as it can get on the ideal gas law side of things, right? So you know how to use the ideal gas law, but I can and will put it together with an equation like this. You have to remember the material we learned previously. Okay. Any questions on that? Okay, there's no questions on that. We have one last thing to talk about here. And this is its own thing. All right. Well, kind of its own thing. PV equals nRT. You can look at this equation. Hopefully you guys can see all of our individual gas laws kind of come from this. You can see how pressure is directly related to temperature. That was Gay-Lussac's law, right? And volume is directly related to temperature. That's Charles's law. And volume is directly related to number of moles. That's Avogadro's law. And pressure and volume are inversely related. So if these things are constant, if one of these goes up, the other one goes down. That's Boyle's law. But there's one relationship we didn't see in those, and that's a relationship between pressure and number of moles. And that's what we're going to investigate as we look at partial pressures. Okay, and I'm gonna copy this figure from your lecture notes over here. And I want you to look at this box that contains 3 different gases, okay? We have some green gas particles, some red gas particles, some blue gas particles. Forgive me, I am a chemist and not an artist, so this is my best representation of a 3-dimensional box containing these gas particles. And these little tails are trying to show that they're zipping all over in all directions, okay? Because they're gas particles. That's what gas particles do. Do you guys see that in my box here? Okay, and some of these are bigger than others, and don't worry about this. But what we see here is the pressure is directly related to the number of moles for any sample of gases. Now this is not, I think, a surprise. Directly related to the number of moles. Hopefully not a surprise, because pressure, as we learned, is collisions, and the more moles of gases you have, the more collisions you're going to have. That makes perfect sense, right? Everything else being the same, if volume and temperature are constant, if I have more moles, I will have more pressure. That makes perfect sense. But what we find that's very interesting, and of course this is related to the fact that all gas particles basically behave the same no matter what they are, is that it's very easy to determine the pressure fraction if we know the mole fraction of what's in here. So if I have a mixture of gases, the partial pressure, that is the pressure of each component gas, is directly proportional to the mole fraction, because pressure is directly proportional to the number of moles. The pressure fraction is directly related to the mole fraction. And essentially what I'm saying here is that here I have a box, and hopefully you count, I did this on purpose, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there's 10 mole particles here, right? And I see 2 out of 10 are green. So we have 20% green gas particles in this box. Everybody agree with that? 3 out of 10 are blue. So that's going to be a 30% of the gas particles in this box are blue. And 5 out of 10 red. That's 50% of the gas particles in this box are red. So this is what I would call the mole fraction. So the relative number of moles of each divided by the total number of moles, right? I'm going to say N of A. Oh, hang on a second. N sub A divided by N tote. Make this smaller. Sorry, I want to make this look neat. So the mole fraction is the number of moles of any component part, we're going to call this A or B or C, or in this case green or blue or red, divided by the total number of moles. That gives you the mole fractions. Okay, so Sarah says, what if I wasn't given a picture like this? Because you're probably not going to be given a picture like this. This is just to kind of simplify it. If you're not given a picture like this, I would have to tell you like the number of moles, right? So that you could calculate the mole fraction, if that makes sense. But what this is telling us is that the mole fraction is equal to the pressure fraction. So that is to say, the pressure exerted by component part A divided by the total pressure, that fraction is equal to the mole fraction. So this is the equation, the important equation to remember here. This one right here. And what it essentially says is if 20% of my particles are green, then 20% of pressure comes from the green gas, and 30% of the overall pressure comes from the blue gas, and 50% of the overall pressure comes from the red gas. That's what this is saying. Does that make sense to you guys? Okay, let's do just a couple of examples just to kind of wrap our minds around this. Okay, so if we know the atmospheric pressure at sea level is 1 atmosphere, and the natural distribution of gases is approximately, we've got 78% nitrogen, 21% oxygen, 1% argon, and a fraction of percent for, say, water and carbon dioxide. All right? So because we know when we have this percentage, these are mole percentages, we can tell that the pressure being exerted, that total 1 atmosphere, 78% of that 1 atmosphere is coming from nitrogen, and 21% of the 1 atmosphere is coming from oxygen, and 1% of that 1 atmosphere is coming from argon. Does that make sense? This is a little bit less of a problem and more of like an illustration here. So here we have this little table. Since we know that in every 1 mole total, this is our fraction, this is our mole fraction. Therefore, we know that for 1 atmosphere of pressure total, this is our pressure fraction. Okay, so here is, okay, here's an actual problem. Sorry. We've got an oxygen tent. Now you could use an oxygen tent to treat patients who like need extra oxygen because they're having a hard time breathing, like if they're a COVID patient. You could either just, put an oxygen line up to them, or you could put them in a tent full of oxygen. A tent is probably less useful if you have a communicable disease, right? You wouldn't want to stuff a bunch of people in a tent that all need help, but you might use less oxygen if you just give them a little line. But if they didn't have a communicable disease, for instance, if you had carbon monoxide poisoning, they might stick you in an oxygen tent. Okay, so here we go. It's just like we're close to 1 atmosphere. So you're not necessarily under pressure, but there's just a lot more oxygen in the tent. It's 45%, instead of 21%. Okay, that's a lot more oxygen. So the question is, what is the pressure exerted by just the oxygen in the tent? if we know the mole fraction of oxygen is 45% and the total pressure is 753. So if we were to use our equation here to solve the problem, let's scroll this down. What they've told us when they say the mole fraction is 45% is that they're telling us that the Na divided by the N tote, that mole fraction is 0.45. Right? And then the total pressure, that's P tote, is 753. So now we could just plug this in. 0.45 is equal to the pressure of A, in this case oxygen, divided by 753 P tote. And we can solve for the partial pressure of the oxygen, or the pressure that's being exerted by just the oxygen, by multiplying 753 by 0.45. And we see that the pressure being exerted by the oxygen is 339 millimeters of mercury. It doesn't need to be in atmosphere. Erica asked, does it need to be in atmospheres? And as you'll see, it doesn't matter whether I'm in millimeters of mercury or atmospheres, so long as I'm consistent. So because this was in millimeters of mercury, this is going to be in millimeters of mercury too. I could convert this to atmospheres and then report the answer in atmospheres as well. Okay, good question. I'm going to bring this problem over from your worksheet. Here we go. We've got a mixture of gases. Contains a number of moles of nitrogen, number of moles of hydrogen, number of moles of ammonia, NH3. Okay. If the total pressure is 2.35 atmospheres, then what is the partial pressure of each component? So I want the partial pressure exerted by nitrogen, the pressure exerted by hydrogen, and the pressure exerted by the ammonia. How should I solve this problem? Zach says, one at a time? Well, yes, but what kind of equation am I going to use? How am I going to set this up? Yeah, so I'm going to use this equation, right? That has the mole fraction and the pressure fraction again. And note, so Na is the number of moles of each component part, right? So like I'm going to have, this is N of N2. I'll do this in a different color. This is N of N2. That's N of A, right? N of H2, because they gave me the number of moles of H2 by itself. And then N number of moles of NH3. Okay? So we know these pieces. What else do we know? .35 atmospheres. What is that? In my equation, what is that? That's my total pressure. Yeah, P tote. It goes right there. Perfect. All right. And the partial pressure is what they want, right? So this is what they're asking me for. So where is this guy? I need the N tote to solve this. You are totally right, Sarah. You just add them all together. The total number of moles is the total number of moles, right? So if you have 1.25 moles of this and 2.05 moles of this plus 3.63 moles of this, then the total number of moles in your sample of gases, because they all behave the same, even though they're wildly different compounds. They all behave the same way, I should say, physically as gases. You've got a total of 6.93 moles of gases, 6.93. That is your N tote. Okay. So now, as Zach says, let's do this one at a time. To solve for N2, I'm going to say 1.25 moles of N2 divided by 6.93 moles tote is equal to the pressure being exerted by the N2 divided by the P tote, which was 2.35 atmospheres. Oh, I violated my own rule, which was solve it before you plug it in. All right, I'm going to multiply both sides by 2.35 atmospheres. And so those will cancel. Perfect, okay. And your moles cancel, right? And you're left with atmospheres of nitrogen. So 2.35 times 1.25 divided by 6.93. Yeah, 0.424 atmospheres of pressure for the nitrogen. Okay, how do we solve it for the hydrogen? Yeah, we're going to play the exact same game, but instead of 1.25 for the moles, we're going to put in 2.05 for the moles, right? So my number of moles of H2, 2.05 moles H2 divided by, again, it's going to be 6.93 moles tote. And I'm going to multiply that by 2.35 atmospheres tote, I should say. So I'm basically setting it up exactly the same way. Divided by, multiplied by. And by the way, you'll notice, you know, your moles cancel and your totes cancel, right? You're left with atmospheres just of hydrogen. So 2.35 times 2.05 divided by 6.93 gives you 0.695 atmospheres of hydrogen. Perfect. So then how are we going to solve this for the NH3? Same thing. I'm just going to use the 3.63 moles of NH3 in there. Perfect. So again, it's going to be 2.35 atmospheres tote multiplied by 3.63 moles of NH3 divided by 6.93 moles tote. There we go. Now again, I've just solved this equation. I haven't resolved the equation. I'm just plugging different things into my solved equation. 2.35 times 3.63 divided by 6.93 gives me 1.23 atmospheres of the NH3. Okay. By the way, at this point you can do a little self-check and say, I know what the total pressure is. So my individual pressure should add up to that total pressure if I did it right. So if I've got 0.424 from the nitrogen, plus 0.695 from the hydrogen, plus 1.23 from the NH3, and I have, yep, because of rounding, it's ever so slightly different, but it's 2.35 atmospheres total. Is my total pressure. There we go. Does that make sense? Perfect. That is it for our second lecture here. We do have a little bit of time, so if you like, we can pull out a problem from the homework, or if any of you guys are like, actually, no, I didn't get that, let's do it again, or let's do a different problem like that. This is a great time to do that. Otherwise, if you are like, nope, I've got this, then I'll let you go. But we do have about 9 minutes here. So probably offset all those times that I ended 3 to 5 minutes late. You're welcome, Sarah. It's just you and me, Erica. Do you want me to go over anything else? The recorder is not responding.